Good morning, everyone. I was just waiting a few seconds to give everyone a chance to get logged in. But in the interest of time, I'm going to go ahead and introduce our session today. Welcome to day 2 of the TESC conference. This session is today's actions for tomorrow's technologies. So we know it's no surprise to anyone that transportation infrastructure has very long lifespans. And so engineers and planners need to be thinking today about what the infrastructure needs to look like in 20, 30, or even 40 years when some of these technologies are realized. And so that's the topic for today. What can we do today to prepare for this technology that we know is not here yet, but is coming? So we'll have three presentations, 4 speakers today. Our first speaker is Barry Einzig, and he is a principal of Econolite CAV Consulting. He's responsible for the business development and the execution of strategic advisory programs for nations, states, cities, local governments, and private corporations. So Barry is going to start us off with how the convergence of ACEs and technology are shaping the future of mobility. Barry?
Thank you. Thank you very much for that introduction. Yes, wanted to start off really this conversation in the broadest construct, and then as we move down through, we'll be able to have specific dialogues from some of our other partners. In this journey, we're really talking about the impact of technologies, not only CAV technologies, but all technologies that are coming into the transportation sector. And I bring up the Gartner hype cycle because it's one of my favorite tools. Some of my favorite language comes out of it. And probably my most favorite is the trough of disillusionment, which you can see in 2019, autonomous driving level 4 was in the trough of disillusionment. We go through these cycles where things get really hot and exciting and sound like they're near term and you need to take care of or do something about them right now. And some of them you do, and some of them you don't. So I want to talk about digitization and sort of a methodology for how you can think about these things. What I wanted to point out on this slide, of course, there's lots of technologies that are coming into the space, but what I wanted to point out on this slide is this is Gartner Hype Cycle's emerging technologies from 2019 and from 2020. In 2019, there are 4 different CAV technology systems that are mentioned that have some time horizon anywhere from 5 to 10 years. In 2020, there are no CAV technologies that are mentioned on the hype cycle, right? So what it means is they didn't go away. It just means they're not being talked about at the same order of magnitude as other technologies that have come along. And through this last few years, as we debate IEEE technologies from 3GPP technologies and connected vehicle systems, one of the favorite comments that came out was, well, you don't want to be Betamax. And so I built this slide to kind of talk about what that really means. Most that remember that history recall that Betamax was a superior technology, but it lost out in market scale, not because it was an inferior technology. And really, if you look at this time horizon, where we sit today, it doesn't really matter, right? Originally we started out with film, we moved to tape, we moved to CDs and DVDs, and then ultimately to digital storage, and then ultimately to streaming services. So, all of these are providing the same services to everybody, but over the period of time, they have evolved. And this is what makes it difficult for the transportation industry because, as Shannon mentioned earlier, we like things to occur over long time horizons and be well planned and, sort of well demonstrated within the standards. And that's not how technology evolves, right? We don't really see those kind of long-term time horizons for technology. So what that leads to is a digital journey. And this is a report that's been updated a couple of times that came out of IMD in the Netherlands. But it's really talking about digitization. Digitization is happening very quickly in private sector organizations, but it is now starting to impact public sector organizations and transportation. And in the 2019 report, it indicated that transportation and logistics as a global industry had moved from 11th place as the most digitally disrupted industry to the 7th. And although 7th sounds like it's still way off, that's behind banking and healthcare and lots of other industries that are having huge impacts. So if you think about the change over that period of time to move from 11th to 7th, you clearly see that we're in that target zone of transportation being greatly disrupted by new and emerging technologies. And why is that the case? Well, it's the case because it impacts, growth and satisfaction of customers. It impacts safety and physical security, asset management and utilization, productivity and supply chain optimization, and most importantly, innovation that's occurring not only in the technologies, but also in the business models associated with these new digital assets. And I put this slide in here because it's a throwback to me almost at this point when we talk about ACEs, right? So 2019 that we were talking about automated, connected, electrified, and shared as almost equal partners, right? Shared got its impact this year with the COVID impacts and quarantining. Electrification seems to be accelerated. Connected seems to be stalled. And automated now seems to be taking its proper place in from a predictive perspective. So a few years ago, everybody talked about these like they were going to all happen from a technology impact at the same time. And now I think we better know that these are evolving over a period of time. So, what does that mean from a transportation practitioners and specifically, within our organizational structures and how we should move forward? So the challenge is we have different views. We have political views from our senior leaders in politics. We have the public's view. We have technology companies' view. We have the traditional, planning and engineering consulting view, and we have a regional impact view. And we need to consider all of these as we move forward because we can't continue to do the same things we've done in the past and expect a different outcome. As you see over my shoulder here, there's a map in the background. That is a 1918 map of the electrified railroads in Pennsylvania. That is considered by most railroad experts to be peak railroad infrastructure in the United States, which means that we still built new railroad infrastructure, but we didn't have more track miles. And so we have to start thinking, are we at peak, mileage for road systems in the United States? And do we now need to pivot to more of a technology application and an operations and maintenance? So how do we move that forward? Well, first of all, technologies tend to be, and that's really why the nail in that screw were on the previous slide, that technology tends to try to jump to the trial phase, right? They don't really kind of understand all the goals and objectives of transportation. They don't necessarily understand the budget cycles and the planning that goes on. But we really need to take a very similar approach to the systems engineering process we've used for everything else. I would say the difference is we need to bring in some of these new digital stakeholders and sort of begin to vet them out so that we can evaluate which ones have real meaning and in what kind of time horizons. There are some things that are very short term and need to be taken care of when it comes to connectivity or data architectures or cloud services. And there are others that are a little further out that come to fully automated systems. So that's my introduction. I would say, we have traditional planning and engineering that needs to take place, but we need to bring in some of the new stakeholders and sort of vet out some of the technology systems and the technology future thought leaders that can really pull these things forward. So if I can help in that in any way, I'm happy to jump in. Shannon, I think turn it back over to you at this point.
Yeah, thanks, Barry. Wonderful. And I forgot to mention, as questions are coming in, you can either send those in the chat or preferably put them in the Q&A. So at the bottom of your screen, there should be a few various buttons. One of them is Q&A. And as those come in, we can answer those either written or at the end of the presentation. Barry, one quick question for you. You talked about kind of going through the process of vetting some of these technologies and working with those vendors. Do you have any tips on how do you go about reaching out to them? Sometimes they don't necessarily want to talk and tell you everything. So what are the strategies that you use to work through the vetting process?
So I think it's a great question. And in reality, what happens is they're communal, just like planners are communal or civil engineers are communal. And so in many cases, finding somebody that's I don't want to call it part of the tribe, but it's sort of being part of the tribe, right? There are people in the industry that have sort of this link between transportation and technology systems, and they're the ones that are in the best position if you don't know somebody to reach out because it's a peer network, right? No different than you would do for a planning idea that you wanted to reach out for another agency. I think that's what makes it a little bit difficult because there's a lack of understanding between the two communities. You need the bridge builders in between those. So it's a great question.
Great, thanks. Yeah, and I saw that you sit on the CARTS committee that's focused on connected and highly automated vehicle systems. So it sounds like you're trying to bridge that gap.
Yes, indeed. Thank you.
All right, our second presentation today is going to come from Abby Morgan. Abby is a senior engineer leading Kittleson's national research on emerging technologies and smart cities. She leads the mobility evaluation of all the US DOT connected vehicle pilot deployments, and she wrote the first national guidebook for state DOTs and local agencies on how to plan for the impacts of new technologies on land use and transportation. So today, Abby's going to be talking about that, how to plan today for the CAVs of tomorrow, specifically on planning level capacity adjustments. Abby?
Thank you, Shannon. And thanks everybody for joining us today. I'm really excited to speak on this panel because I think we've got some great topics that all overlap. A lot of what Barry was just introducing is much of what we're trying to plan for right now. Those impacts of new technologies that are coming our way that we might not understand completely about yet. So what I wanted to do was just first introduce myself. So as Shannon said, I'm with Kittleson and Associates. I'm based out of our DC office, and I work mostly on our connected and automated vehicle projects. The project that I wanted to focus on today was helping us understand specifically capacity impacts that new technologies, primarily connected and automated vehicles, will have, and how that integrates into our planning solutions and what agencies can start doing about that today. So I'm going to walk you through the need, much of which Barry set up perfectly for me. You know, why are we asking these questions today? And then for the project that we're working on, what sort of assumptions do we make about vehicle technology, about its timeline for adoption? And finally, how can you expect to implement the strategies and the results that we've got from this research? So as Barry mentioned in his presentation, you know, we are required to think about the future today. So we need to develop state transportation improvement programs, regional transportation improvement programs. And when we start doing that, we're really expected to plan out our 2045 or even 2050 planning horizon. What will be the growth that we expect? What kind of capacity do we need? And we're making decisions today to find funding sources for things like, do we need to widen our roadway? If we have a 4-lane highway that's at capacity, do we need to widen it to 6 to 8 lanes? And we're trying to make all of those decisions today so we can set up our funding so that we're ready to make those improvements in the future. But what we're missing from that equation in a lot of ways is what are going to be the impacts of new technologies? Do we need to continue widening roads, or can we instead use technologies to our advantage as a tool to help us, for example, make capacity more efficient than it is? Well, one of the problems that we've identified as we've started down this path of work to understand the capacity impacts of connected and automated vehicles is that to date, most of the research that exists considers the impacts of vehicles in very isolated scenarios. We call them pipeline freeways. So single lane facilities that have no friction points, no on or off ramps, no intersections, really no opportunities for passing and lane changing, which is not the reality of what we actually need to face, right? So connected and automated vehicles that will be entering into our environment will be entering into real world scenarios. They'll be interacting for quite some time with human driven vehicles, possibly with other road users, pedestrians or bicyclists if they're in an urban environment. And there are some strategies that we can take today to artificially increase our penetration rates of connected and automated vehicles. Things like doing managed lanes, where we would actually start to think about, you know, how can we dedicate a lane for automated vehicle use only? And while we're still kind of at lower overall penetration rates of these technologies, maybe we artificially increase their rates by dedicating lanes to them. So we're thinking about all these scenarios. And what this really emphasizes is that scenario planning is vital as we move forward to try to understand what these impacts will be, what different scenarios and strategies we can do. So this isn't just what technology is coming, but it's also how can the agencies incentivize its adoption or its penetration rates in our systems. The project that we're working on right now is a pooled funds study. It's being led by the Oregon Department of Transportation. And what we're working on specifically is looking at the impacts that connected and automated vehicles will have on capacity so that we can actually develop capacity adjustment factors that are going into the highway capacity manual. So we've been working on this project with a group of supporting state DOTs, as well as our research partners at UCLA to really understand and create new chapters that are going to be part of the next update of the HCM 6.1, which is coming out next year. One of the key assumptions that we are making in this study is we are looking at vehicles that are connected and automated. So when we think about the technology types that are out there, and much of the technology Barry introduced to us, we're talking about vehicles that have onboard sensors. So that could be camera, radar, LiDAR, different types of technology that help them understand and observe their surroundings so that we can have automated driving systems take control of the vehicle for what a human driver is responsible to do today. The second key component that we're focusing on in this study is the connected aspect. So we're also assuming that these vehicles are able to communicate with each other or with the roadside environment so that they gain a better understanding or a more advanced understanding of their surroundings. When we combine these two, the connected and the automated approach, we can make assumptions that the vehicles will be able to not just do things that we have today, like adaptive cruise control, where a radar or camera or LiDAR sensor can help a vehicle maintain a safe following distance and speed, but that they can do that in cooperative fashion, that they communicate with the vehicles that are in front of them, and they ultimately are able to form platoons. So this is a real key that we're studying in this research, is what are the impacts of platoons on freeway segments, on arterial segments, and what happens when we're interacting with human drivers where we aren't platooning, that adaptive cruise control setting versus cooperative adaptive. So this is what we're looking at right now, is what will be the impacts on capacity of vehicles that have these automated features and are working in mixed environments. So we have to think about what our timeline will be. And we can take a bunch of different approaches to this. I like the research Todd Lippman has put together on his prediction of automated vehicle adoption timelines. And really what we're seeing is that it's going to take quite a bit of time. You know, as Barry said, we're in that trough of disillusionment. We're not at that super high acceleration of technology advancement or interest right now. But the other challenge that we face is that not only do we have to wait for this technology to become real world ready to be put in the hands of consumers, once it is ready, our US light duty vehicle fleet takes about 14.8, let's just call it 14 years to turn over. So we not only are waiting for the technology to evolve to a point where it's widespread ready, we're also waiting for a point when we have a turnover in the vehicle fleet that would lead to higher penetrations that we would expect to see on the roads. So again, we can wait for this to happen naturally for our whole fleet to turn over, which will take time if it ever does fully turn over. Or we can do things to incentivize the adoption. And that's another thing local agencies can do. So incentivize adoption of the fleet in our sales, or incentivize it by creating these environments for AV only lanes and things. So really what we're seeing though is that in our 2040, 2050 planning horizon that we're focusing on right now, there will still be human-driven vehicles that are out there. And so we want to understand, again, that interaction in that mixed fleet and what capacity assumptions we can make. So what we did was we looked at many real-world segment types. We looked at freeway segments, and not just a basic freeway segment. We looked at a merge segment, weave segments. We also looked at arterials. So we looked at signalized intersections with protected or permissive turning movements. We've looked at two-way stop controls and at roundabouts. I don't have time to share all of those results with you today, so I want to focus just on the basic freeway segment to help you understand some of the impacts we're seeing. The really exciting thing that we saw was that as we increase our market penetration rate of connected and automated vehicles in the fleet on this segment, we are seeing a steady increase in capacity. So this is really what we hoped to see, what we expected to see, is that capacity can be increased as we get larger market penetration rates of connected and automated vehicles. But as I said before, we looked at what happens if you're platooning or if you're not. And what was really interesting was that when we considered the impacts when you're platooning at different levels of aggressiveness, different following headways, and we compared those when you're not platooning. So a vehicle that is just using adaptive cruise control, not cooperative, so it's not communicating with the other vehicles, it's not platooning up. That adaptive system is much more conservative even than human drivers are today. Think about the liability that we're seeing, the liability risks that a manufacturer might not want to take on. So if we don't support a cooperative future where vehicles are able to communicate with each other and with the roadside, we actually see that we might have a decrease in capacity in the future, just because of this very conservative nature that we see from the systems that are available today. So what do we do? Where are our results going and what can you expect to see? As I said, again, we're updating the chapters in the next edition of the HCM 6.1. And you'll see results in two different ways. First, you'll see capacity adjustment factors, and these summarize kind of the percent increase that we're seeing for different systems. So when we just focus again on the basic freeway segments, what we're seeing is that if we take our standard freeway starting capacity of 2,400 vehicles per hour per lane, we're seeing about a 30% increase if we were to have an AV only scenario, a connected and automated only scenario of 100% penetration. So, moving out to the future, maybe we see up to about 30% increase. This is a bit lower than what some of the forecasts were initially predicting. But when we actually start looking at different freeway types that have lower starting capacities, we see that there's a much greater impact of these connected and automated vehicles. So if we think about that, we're expecting that connected and automated vehicles won't be as affected by things like narrow lane widths or maybe vertical grades. So we actually see up to 70, 80% increase in capacity when we have connected and automated vehicles on these lower base capacity roadway segments. That's really exciting, and it's something that we want to continue tracking once we put these vehicles in the hands of consumers to understand what happens in the real world. The next example of how the results will be shared with you is in simple daily service volume lookup tables. So again, scenario planning is going to be key. What we're doing here is we're helping to think about what scenarios we would expect to see in our future. And we aren't going to be able to pick just one. We want to pick a couple, but we'll be able to look at these lookup tables to help you understand what capacity increases you would expect to see over time as your penetration rates increase. And finally, we can put the two together. We can put together our timeline of when we expect to see the adoption of this technology. We can put together the capacity increases that we expect to see. And what we end up getting is kind of the convergence of the two helps us understand sort of the upper and lower bounds of what we might expect to have for our capacity adjustments. So again, these are kind of those bookend thresholds of where our scenario planning would take us over time and with our different adoption patterns that we would expect to see. So what should an agency do with all of this? Well, again, we need to start asking these questions today because we have to plan for a longer term horizon. That 2045 long range plan is already something we need to do today. So we need to think about what assumptions are right for our local communities, for our states or our regions. What sort of technology do we expect to implement? What are we expecting to support and make sure that we maintain that type of equipment, thinking through the maintenance programs that we need to support these different futures? Well, what an agency can really start doing to help them plan for this uncertainty is to self-assess. Look internally at your staffing, your resources, as well as really just your readiness of your policies to support these new systems. And are there any sort of policies that you can use to help incentivize a quicker adoption? The next thing we want to do is get data. As we have all these new technologies, we want to collect and most importantly, monitor that data so that we understand what is really happening in the real world. There's been such limited availability of these types of systems really in our real world vehicle fleets. We want to get that data and understand how capacity truly is being impacted. We also want to get smart. Barry mentioned, this is not something that we can do in isolation anymore. We have to reach out to the community. We have to get new stakeholders involved in our planning process. Industry to help us understand how the technology is being deployed, but also other departments, the maintenance departments, law enforcement, and first responders who will be getting some of the most interesting real world understanding of these vehicles once we put them into consumers' hands. And really start collecting good partnerships with many diverse stakeholders so you can understand and look at these types of impacts and capacity from all sides. And finally, be nimble. We're going to have a great learning opportunity as we start to adapt these new technologies and as we start planning for them. So help make sure your policy can be flexible, your staff is empowered to make changes as we learn from new technologies that are in the field. So I'm really excited to see the rest of our discussion today and hope that this gives you sort of a snapshot of what we expect to see with some of the capacity changes from new technologies. So thanks very much, and I'll turn it back over to you, Shannon.
Thanks, Abby. And again, as folks have questions, feel free to throw those in the Q&A session too. Abby, we were chatting yesterday, and you were mentioning that there were some like low-hanging fruits that a lot of agencies can address when it comes to kind of being prepared, especially if they're not going to be at the forefront of, they're not Washington, D.C. going to be seeing the first launches of some of these technologies. Could you give a couple of examples of things that municipalities or agencies should be thinking about?
Yeah, absolutely, Shannon. I think one of the things that we need to recognize from that timeline is really that there are going to be human drivers in the fleet that we need to continue to provide safe and efficient transportation for. And so if we think about the different types of investments we can make, think about ones that will benefit the human drivers today as well as the technology of tomorrow. So a couple of the studies that I really like are ones that are looking at lane line quality, because today we have lane keeping assist systems that are able to monitor and detect lane line and already start doing some of that automated driving. But there are many cases where our lane markings are so poorly maintained that those systems can't even work today. So if we expect a vehicle of the future to be able to drive on our roads, why not benefit all drivers, human drivers, who also could benefit from seeing the lane markings and staying on the road and the pavements, as well as the sensor technology we have today that we're already learning from. So things like pavement marking, it's not the most exciting thing, maybe, but you can get so much cool data from these vehicles to know exactly when they can see or can't see, that we can get really well-informed maintenance programs for things like our pavement marking. And when we start talking later about signal systems, I think that's another thing. There are already some really neat advances we can do today that new vehicles that are able to communicate with our infrastructure will only benefit more, either from knowing things about the infrastructure, the signal timing ahead, or that we can learn from them, knowing exactly when they're coming and what platoon. So I'm really excited to see those types of low-hanging fruits.
Yeah. So it sounds like maybe we can use the new technologies as a way to get our politicians to beef up the maintenance budgets. So.
Yes, have to focus on maintenance.
Yes, yeah. All right, thanks, Abby. Our third presentation today is we're kind of zooming in. So we started broad at the technology overview. Abby gave us kind of planning levels. We're going to jump now into a very discrete traffic signal. So preparing for tomorrow's traffic signals today. This presentation is by Anthony Castellone and by Ozan Tongus. So Anthony is a senior TSMO engineer in Panone's Clearwater, Florida office. He has over 35 years of wide-ranging experience in all phases of transportation engineering, including complete streets, transportation planning analysis, highway capacity analysis, traffic signal design, ITS, signing, pavement markings, like Abby just mentioned, and coordinated system signal timing. And Ozan is the founder, CEO, and CTO of the Carnegie Mellon University startup Virtual Traffic Lights. He's also the co-founder and CEO of another CMU startup known as Retrofit AI. And he is a tenured full professor in the Department of Electrical and Computer Engineering at Carnegie Mellon University. So I will turn it over to Anthony to kick off our third presentation.
Well, good morning, almost afternoon here, and we're going to jump right into this. This presentation was presented previously at APC last year, and we had such good feedback. We had folks that came back and said, we want to hear more about the virtual traffic signals. And so Ozan and I put this together, but we're going to start with a little video for those that are on the presentation this morning.
How about a ride, mister?
Jennifer. Oh man, you a sight for sore eyes. Let me look at you.
Marty, you're acting like you haven't seen me in a week.
I haven't.
Are you okay? Is everything all right?
Oh yeah. Everything's great.
Marty! You gotta come back with me.
Where?
Back to the future.
Wait a minute, what are you doing, Doc?
I need fuel. Go ahead, quick! Get in the car!
No, look, Doc, I just got here. Okay, Jennifer's here. We're gonna take the new truck for a spin.
Well, bring her along. This concerns her, too.
Wait a minute, Doc, what are you talking about? And what happens to us in the future? What, do we become assholes or something?
Oh, no. You and Jennifer both turn out fine. It's your kids, Marty. Something's gotta be done about your kids.
Hey, Doc, you better back up. We don't have enough road to get up to 88.
Roads? Where we're going, we don't need roads.
Hey, Marty! Marty! Marty, I wanted to show you these new matchbooks for my auto detailing I had printed up.
Like the DeLorean?
What the hell is going on here?
So very interesting. If some of you remember that movie, it may not be so far-fetched as we think about the need for traffic signals. If we don't have roads and we don't have intersections, do we need traffic signals? We're going to talk a little bit today about how we transition, how the traffic signal has transitioned from the horse and buggy days. And by the way, Boeing, the flying car is not so far-fetched. Boeing, in conjunction with Porsche, has been in competition with other companies to build aerial vehicles that could make vertical takeoffs and landings. So let's get started and revisit the history of the traffic signal, starting in the late 1800s, just after the Civil War, with the first gaslit signal in London. Those were called semaphore arms, and they were red and green only. That went to an electric traffic light, the first one being in Euclid Avenue, on Euclid Avenue at 105th Street in Cleveland, Ohio, in 1914. And then in the 20s, we had our first four-way, three-color red, orange, or yellow, green traffic lights. And 50s, you saw the the phenomenal innovation of the electromechanical timers that were introduced. So rather than just being a simple green, red, pre-timed, you could actually put different cycles into a 60-second or more cycle length. And then in the early 60s, we got into computerized traffic signal control. And in the mid-70s, NEMA introduced the first solid state controllers in the US. And there's a picture of an old dial on the top and one of your NEMA controllers on the bottom there. The 70s also saw the UTCS software, control software, which was primarily utilized for traffic signal systems within a CBD city environment. In the 80s, the NTCIP protocol started introducing our advanced transportation controllers, and then the NEMA TS1 graduated to TS2, and we've in the 90s we saw LED and countdown timers. There were different systems of adapting to traffic congestion in real time, and those traffic responsive signal systems, SCOOT and SCAT, some of them are still around. In the 2000s, we started seeing the first smart signals. Those are your adaptive traffic signal controls and systems, and of course the 2010s, the big data, and particularly the data collection and capabilities of Bluetooth and microwave, and in addition to loops, just was fuel for the smart signals and the smart signal communities that we're talking about, smart cities. The ability to look at real-time performance measures, actively manage traffic signals through our advanced traffic management centers, ATMS systems. And as I mentioned, the ATSC, adaptive traffic signal control, has been more prevalent. And with the use of advanced transportation controllers, we jumped into the 2020s with smart corridors, and that was initiated via the USDOT SPAT challenge. But we still have signal challenges with the smart signal, with the adaptive signals. And some of those challenges are that black box mentality, that you just set it and forget it and let the adaptive signal do all the work and all your coordination. But there are maintenance costs involved. There's never a one size fits all, and a lot of the adaptive traffic systems are not really AI ready. So as we transition from the legacy equipment to the Internet of Things, again, as I mentioned earlier, the USDOT with the SPAT challenge introduced 50 states to look at intersections using the DSRC infrastructure to really provide that smart corridor and utilize the technology to its fullest. So where are we going? You know, we talk about a 2045 planning horizon. Our roadway designers typically look at a 20-year design horizon, but at this pace that technology is evolving, even 5 years seems to be way out there. So we're looking at a 10-year forecast, you know, it signals that, you know, as connected vehicles become penetrated, as mentioned by Abby, you know, 10 years is like, it is the technology innovation that we have to adapt to today. So, and we feel that traffic signals will become virtual before we start eliminating intersections as the video portends that I showed. So with that, I'm going to introduce Ozon and the virtual traffic light technology that he and his firm in conjunction with CMU have worked on. So Ozon.
Yeah, thank you so much, Anthony. I am fascinated with the speakers today and the amazing presentations. So as a CMU startup, we have been working on this disruptive technology. The key idea was actually to leverage initially the presence of this DSRC technology that Anthony mentioned. As you know, that technology was initially invented probably about 20 years ago as a means to increase safety, both in urban areas, on highways, etc. So what we did as a new technology company was to ask a fundamental question, which was, how do we take that, if it's going to be in every car eventually, and make sure that we can use it for traffic management? So if these radios will be in every car, and it will not be, it will be independent of the drivers, irrespective of what the drivers are going to do, they will be there sending beacon messages every 100 milliseconds, reporting the location, the acceleration, the speed, and the trajectory of every vehicle. So we asked if that's already there, what would it take to use the same radio communications, or what we call V2V, vehicle to vehicle and vehicle to infrastructure, like Anthony mentioned, to essentially manage traffic flows in urban areas where there are points of conflict, which essentially means that there are two competing flows, and we have to give the right of way to one of them. But the idea was, can we do this without traffic lights, right? And we answered that in an affirmative way, and we said that yes, you can. And we developed a technology which has been showcased in field trials, both in Pittsburgh and in the Gulf region several times. So Anthony, if I may go back to the previous slide. So let me briefly mention what's going on. So this picture here depicts how the technology at a fundamental level works, A, B, C, and D. What you are seeing here is different vehicles approaching an intersection, and through V2V communications, they become aware of each other's presence, their distances from the center of the intersection, their speeds, accelerations, etc. And based on some of those constraints, like in many other distributed protocols, they make a decision as to who will be the leader and who will replace an infrastructure-based traffic light. That in part B is shown as the blue vehicle. So once that leader election is made, then that leader behaves like a infrastructure-based traffic light temporarily, and gives its own approach a red light, and the opposing flow or the orthogonal direction a green light. After some time, so that's shown in part C, after some time that responsibility is transferred or handed over to the other direction. Now you see the leader or the virtual traffic light in part D in the north-south direction or approach. So that's roughly the idea. So we have, why is this very interesting? Because this holds the promise of essentially having traffic control in a seamless manner in all parts of a city. Just so that we are on the same page, in Pittsburgh, for example, out of 2,100 intersections, only 316 are equipped intersections with traffic lights. With a technology like this, the potential is you have traffic control at every intersection. So then, without going into details, when we were talking to certain investors, they said, yeah, but for this, you need all vehicles to be equipped with your radios. So this is what we call full penetration problem. So to solve this problem, then we developed the technology to deal with partial penetration. In other words, if you have 5%, 10% of vehicles in Pittsburgh or Boston, which have DSRC radios, would VTL, virtual traffic lights technology, work? And it will, provided you put on each of these traffic lights a roadside unit. So in that case, in an approach, you'll have a mixed scenario. The blue vehicle here has a radio, the red vehicle does not. The blue vehicle can actuate that traffic light to turn green. And in that way, the red vehicle will essentially benefit from that also, even though it's not equipped with that radio. So this way also, we have shown that VTL can function with partial penetration. So we did a major field trial at Riyadh Airport in February. And one of the complaints about this beautiful technology known as V2X based on DSRC is that for the time being, it looks a little bit expensive. So people are saying putting these radios at a price tag of $1,000 per vehicle is a little bit too much. So that forced us to kind of import this technology to smartphones. And then we essentially developed the technology so that it can work with things like 3G, 4G, LTE, LTE Advanced, 5G, etc., whereby a smartphone or a very similar device, remember Vodafone sells smartphones for $35 in Africa. So for a smartphone device, essentially sending these messages, which talks about its location, GPS location, etc. Now we are taking all this information to the cloud. The decision making is done in the cloud based on VTL's proprietary algorithms, as this diagram is showing. And then like a rain, it showers back onto each intersection where all the vehicles become aware through that smartphone what is the current traffic light. So they're still seeing on their device that they have a red light or green light. So we call this, we have a new product, which is known as TrafFluid. This comes from the notion of traffic and fluid traffic. The idea here is essentially carrying all the intelligence that's needed and currently exists in places like central offices to the cloud. And the cloud makes the decision and then relays it back to the urban area, or for that matter, even highways and other places. So this new slide shows how this is shown as an app on a smartphone. It's pretty simple and seamless for the end user. Having said that, I think it's important to mention that we are using currently Google Cloud Platform. But in addition to the basic services that Google Cloud provides, as a company, we have written a huge software, something of the order of 100,000 lines of code, which essentially is responsible for this decision making. Mind you, the technology that we developed and this software can run on any cloud platform. So you can also take Microsoft Azure or AWS, Amazon Web Services, it would still work. So we are very excited about this technology because yesterday I mentioned that in urban areas, this can reduce commute times by 40 to 60% during rush hours, which is phenomenal. It can significantly decrease the number of traffic accidents because of this V2X technology. So vehicles which might run into an accident very quickly will be able to avoid the accident. It can be used for mass transit. It can be used for closed and controlled spaces like airports, warehouses, military bases, university campuses, etc. So some of those benefits are shown here. What I would like to emphasize is that this holds the promise of having traffic control at every intersection. Just to give a statistic, New York City, the Big Apple, has got 24% of its intersections equipped with traffic lights. The rest of the intersections, 76%, does not have traffic lights because it's a very expensive proposition, right? I mentioned to Pennoni that it costs $200K, and so, an engineer in Pennoni corrected me saying he wished it's much more than that. He said it's probably of the order of 300, 400, maybe more, depending on what kind of intersection. So this is phenomenal, because if we can reduce the time that vehicles are on the road to be less, that means that the carbon footprint of vehicles, or in cities, the carbon footprint will go down. So that essentially leads to a greener environment. If I give you time back, unlike an AV, you can go home 1/3 of the time less and take your dog for a walk. You can go to a pub to have a beer. You can take your girlfriend or wife or husband to dinner, right? The freedom that AVs give is confined to the vehicle. So you cannot play tennis in an autonomous vehicle. You see what I'm saying? So this is time without strings attached when you go home, right? So, to wrap up, we are ready for prime time. So we have this product ready to be deployed. It's a very cheap technology, probably 10x or 100x is what we are talking about, cheaper than what currently people are doing. It's the thing which makes sense. All businesses are migrating towards the cloud and AI. So using AI on the cloud holds the promise of optimizing traffic flows through some AI algorithms such as reinforcement learning, and making this cheap and ubiquitous everywhere in urban areas and on highways. Reduce the number of accidents dramatically. So this is, for example, when we went to the Gulf region, they showed more interest to this aspect than reducing commute time, because they told me, they said, Ozan, compared to US, per 1,000 vehicles, the number of accidents is like 3 times more in the Gulf region, because when people are in a vehicle, they think they're in a helicopter. So they want to fly, right? And that, of course, leads to accidents. So you need a technology to take care of this. Even in US, we are talking about 38,000 fatalities per year. Hundreds of billions of dollars lost in these accidents and medical bills, and people getting crippled, and social welfare has to take care of them, etc. So let me stop here with the promise that VTL is very proud to, just like Abby mentioned and Barry mentioned before, that cooperation between vehicles, right, through V2X, using AI for decision making, right, and bringing the power of the cloud that is being supported by, you know, the Googles and Amazons and Microsofts and even IBMs, is the way to go. This combination is invincible. I mean, we have a paradigm shift. So let me stop there so that there might be some questions.
Great, thanks, Ozan and Anthony. And one question here real quick is, so if the vehicles are acting as the controller, what is the status of the intersection when there are no vehicles present, but perhaps pedestrians are present? Does it then become a situation where the vehicles, any vehicle that does approach then would recognize the pedestrian and yield to them, or how does the pedestrian know the status of the intersection when no vehicles are there?
So we have some proprietary technology on that also. But there are different ways of dealing with that. So if there are no vehicles approaching the intersection, then there is no trouble in terms of pedestrians crossing the road, right? The trouble is when vehicles are communicating with each other, but the pedestrians also need to know what's the who has the right of way, and that can be interfaced through, for example, current vehicles, contemporary vehicles have got their mirrors, and underneath the mirror, we are showing that this vehicle is turning left now. So, for example, a very simple interface, which essentially lights up a pedestrian sign, could indicate to these pedestrians that it's their turn. And if there are no vehicles, then there is no conflict, so the pedestrians can safely cross the road. But there are quite a few ways that we have worked on so far, so that problem is solved within our technology.
Wonderful. And we just had a question come in. I saw see Abby is typing away, and so maybe Abby or Barry, you can chime in on this. But Steve says, this is a great session and good information. Since this does address the future, how do we get all this collected information in front of everyone for consideration? As in the past, too much effort can be spent going in one direction, and maybe that direction is not set as a standard or the way for global acceptance. How do we get in front of everyone? So Barry, maybe I'll send that to you. How do we kind of wrangle all of this and get everyone, all the cats moving in one direction?
Thank you for that. So that's really why I pointed to the digital journey. There's a methodology for this, just like there's a methodology for any other engineering systems. It's really about considering all of the different technologies and mapping them to your goals and objectives of the organization. What I see in a lot of these technology solutions that people are piloting is they don't map to the goals of the organization. And so therefore they wind up failing, because even if they're successful, they don't mean anything for the long-term impact of the organization. And I think that's where the disconnect is. And I think if we start with a digital journey, start with a plan that maps technology to the outcomes that you're trying to deliver as an agency, then we can test and validate the proper ones in the proper time frame.
Got it. Abby, anything to add?
I agree completely, Barry. I think you nailed it. The way I like to think about this, technology is a tool. The deployment of technology is not our goal. It's our tool, and our goals are safety, our mobility, equity, sustainability. So this is just one of the many tools that we have in our toolbox, and the goals should align with our overall agency goals for transportation.
Great. And then 2 questions that came in for Anthony and Ozan specifically. The first, is there any thought of people being able to pay the virtual lights to have preference for their vehicle if perhaps they pay more than others? And then also, is the technology currently deployed anywhere in the US? So you mentioned that it was piloted in Pittsburgh. Is it still active there?
Right.
Ozan, I'll turn that over to you, since it sounds like someone's thinking, like the hot lanes where you can pay to beat all the congestion on the freeway. Would
Right.
you be able to prioritize that for the signal preference?
Well, I'm not sure I understood the question. Is the question, can someone play the system or bribe the system so that they can get advantage?
So in your optimization strategy, could you envision adding a component where there's a payment incentive? So if you pay more, your vehicle is ranked higher in priority.
Absolutely. So that's why initially I talked about the partial penetration problem. So, for example, if you take that scenario within the current state of affairs, and if we don't touch the traffic lights, anyone who has his vehicle equipped with this application and technology will have the upper hand. But if you live in an apartment complex with a neighbor who goes to downtown Pittsburgh, and his commute is like, 15 minutes less than yours, that's a very strong incentive for you also to put the same system into your vehicle. So I mean, I want to answer that question like that. And
there's another one too, Ozan, on whether your technology has been deployed anywhere in the US. So I know you have a more than a prototype. You have a working virtual traffic signal device.
Right.
So is it deployed anywhere yet in the US?
So, so we have done field trials and demos both in Pittsburgh and in the Gulf region, but it's not deployed at a state level or local authority level. That's what we are looking for. That's the next step. We want to work with you guys to take that big next step, because our technology and products are ready at this point. So we are looking for large-scale deployment. We have been talking to Utah Department of Transportation and also Pennoni so far to help us bring this technology to the marketplace. So.
Great, thanks. And thanks to all of our panelists. We are at 12:30, so we're going to wrap up here so everyone can head to lunch before the next 1 o'clock sessions. But I would encourage you to continue this conversation in the lounge, or if you would like to get in touch with any of our presenters, shoot them an email, or Penn State has said that you can send them an email at the TESC email link if you aren't sure how to get in touch with the presenters, and they'll help connect you. So thanks everyone, and enjoy the rest of the conference.
Thank you. Have a nice one. Bye now.
Bye-bye.
Bye-bye. Thank you.